All right, dude, we are live. What's up, guys? This is Dem Keys, and holy shit, we are doing a sixth talking stream in a row. I finally managed to say that properly because the past few times that I tried to celebrate the fact that I was doing multiple talking streams in a row, each time I would just not know how to form that sentence. But yeah, dude, we are doing our sixth talking stream in a row. And I'm hoping to just keep this. Well, okay, I don't want to say that I'm hoping to keep this streak going. If the streak keeps going, awesome, great. But at the very least, I want to minimize the number of days that I don't do talking streams. So basically, I want to do as many talking streams as possible, and I mean, hopefully, each stream is also going to be as productive as yesterday's stream. In yesterday's stream, we dove into cross entropy loss and tried to understand what the oh god, hold on, give me a second. Okay, yeah. Sorry, I had Fillion's stream on another screen, and she just screamed. Okay, so what was I saying? What was I saying? Give me a second. Let me mute this so that I can. Okay, so what was I saying? Yeah, yesterday we dove into cross entropy loss to try and understand the algorithm or the collection of algorithms that make up cross entropy loss and what exactly happens during that process and what what the loss represents. We dove into all of that stuff. Check out yesterday's stream. It was, dude, it was a productive stream in terms of learning because I learned so much. It was, dude. Okay, so after yesterday's stream, I carried on. I actually got busy doing some other stuff, and I kind of carried on reading up on this stuff. I was trying to understand where is it? The training code. We'll start reading this whole thing like from the beginning. But like at this point we are past the loss function. Now we need to go into the optimizer and well loss start backward as well, which is where I believe the gradients are calculated. After that, we do the optimizer step. So okay, I was towards the end of yesterday's stream, I was trying to understand exactly what is going on here and what kind of output this is going to be producing. And then I looked at the output, which is here. And I was kind of confused looking at this initially because I was like, okay, hold up. There's each batch contains 64 samples, right? And we have we have batched or chunked up. I'm not sure how to. So we've segmented the data set into batches of 64. So the batch size is 64, and if I remember right, that makes the total number of batches around somewhere at 900 something. Hold on, let me just get the exact number. So what is it? 64? No, it's 60,000 samples divided by 64. Uh, okay, let me just comment out all this code. Right. Give this thing a second. Okay, yeah. For a second, I was gonna be like, yeah, give this a second because it's getting stuck. But yeah, we're good. So let me just comment out all this. Maybe I should refresh this page because I haven't touched this a whole lot since yesterday, and because of that, I think it's a little slow. Okay, so it's let's say 938 samples. If we divide 60,000 samples into batches of 64, it's around 938 samples, right? So I was kind of confused by what we were seeing here. I was like, how does this make sense? But then I also looked at, where is it? Here, I think. Yeah, this is the train loop. I then also looked at this and I tried to remember what the modulo operator does. And dude, this is kind of interesting because the modulo operator, you can think of it as sort of a wrapping operator. You can use it to wrap values around a certain, or well, wrap values around a certain uh, range. So, for example, actually, I can give you a practical example here, right? So, oh God. Okay. All right. So, let's say we do 1 modulo 10. That's 1, right? And well, 0 would be 0. If we do 5 modulo 10, that's 5. If we do 9, that's 9. But watch what happens when we do 10. It goes back to 0. And then if we do 13, now it's 3. 14, now it's 4. 19, now it's 9. If we go to 20, it goes back to 0. This is what I was talking about. This is what I was talking about when I said that it's sort of a wrapping operator. You can use it to wrap values around a certain range. So in this case, what we are saying is that we want to wrap whatever the value is around the range of 0 to 10. Actually, hold on. Let me just confirm something here. Okay. Let's do 20 and then let's do 40. Yeah. So what we are saying is that we want to wrap we want to wrap whatever the input value is within the range of 0 to 20. And we're not necessarily clamping the value between that range. We are wrapping it. The reason I say wrapping is because it sort of restarts back from 0 at a certain point. That's kind of why I'm saying wrapping around. If it was just clamping, then it would just stop the value there. That's why I'm not using the term clamping. So yeah. Anyways, that's how the modulo operator works. And when I noticed this, I was like, okay, hold on. Let me think about this for a second, and then it made sense. So what's happening here is that every 100 samples, it calculates this loss kind of thing. Yeah, every 100 samples, it calculates this loss kind of thing, and it's still like iterating over the entire 900 something samples, and it's using all of those samples. Well, no, it's iterating over the 900 something batches, and in each batch there's 64 samples. So it's running through all of those samples and it's doing its training process. But in terms of calculating the loss, we are only doing that every 100 samples. And if we take it in that way, then if we have, wait, did I say 100 samples? No, it's only calculating the loss, or well, no, it's printing out. It's printing out the loss every 100 batches, not 100 samples, because each batch contains 64 samples. So it's only calculating, or well, not calculating. It's only printing out. It's only printing out this loss and current and all of this stuff every 100 batches. So if you consider that there's 938 batches in total. If you try to divide this up into groups of 100, you'll have 10 groups. Or if you try to divide this up into batches of 100, you'll have 10 batches, and that's why we have 10 statements here. And yeah. So we have, and this is just one epoch. This is uh, one iteration of the training phase where it iterates over all of the training samples in this one iteration, this one epoch. And just like this, we have 10 epochs in total that happen or that take place. There's 10 iterations, 10 such training iterations that happen, and you can see the accuracy of the model and the average loss hopefully reducing each time. So look at this. The accuracy in the first epoch, it's 50%, around 50%. Average loss is 2 point something. Second epoch, accuracy 55%, close to 56%. And the average loss is now 1.9, so it's gone down. Third epoch, hold on. Yeah, third epoch, 58%. Losses, average loss is lower. Fourth, 60% accuracy, average loss is 1.2, so it's going even lower. And then as we keep going lower and lower, the accuracy keeps going up and the average loss keeps going down until we hit the 10th epoch, where this is our average, this is our accuracy, and this is our average loss. So if we give it more training cycles, it would hopefully get to the point where the accuracy is perfect and the loss is incredibly low. Though, I think this is where we need to consider the concept of overfitting. So I need to find out how much is too much training. Like at what point should we stop the training before the model starts overfitting to its training data. I guess all of that we're going to be reading it here. Oh, I guess not. So this just covers the entire training process. Where exactly does overfitting get covered? Optimization loop. Okay. Loss function, optimization algorithm. So in this case, we're going to be looking at stochastic gradient descent. I don't know to what extent I'm going to be able to dive into the math for this. So I'm going to try and get uh, a high level overview. And if it's possible, then I'll dive into the math for it. But for the time being, I just want to get a sort of understanding of what is happening here. Because from what I understand, stochastic gradient descent uses the gradients to calculate how much we are supposed to change the weights and biases. Let me just Google something real quick. Give me a second. Okay, PyTorch, overfitting. Let's see if there's any documentation on that. How to handle overfitting properly. Increase the dataset size. Okay. How to prevent overfitting. Use a weighted sampler. Top 15 methods to avoid overfitting. Okay. I feel like this is the part where I should probably ask a language model to explain overfitting. And yeah, now I can switch back from BRB. Okay, so give it a second. Let me also refresh this page so we can, like, have a whole new conversation. Give it a couple of seconds because I haven't touched this browser since yesterday, so things are going to be a tiny bit slow. Okay, are we good? I think so. Okay, I'm learning deep learning I'm learning about building and training FCNNs. I'm sticking specifically to feed forward neural networks because I also need to look into the concept of overfitting when it comes to something like linear regression. But for the time being, I'll just keep it to feed forward neural networks. I'm sure this applies to um, others as well, convolutional neural networks and transformer based networks and stuff like that. There's probably going to be overfitting situations there as well, and there's going to be different ways to handle overfitting there. Or who knows, maybe some of those architectures just out of the box they prevent overfitting. I'm not sure. I don't know. We'll find out once we go into those architectures. Okay, so I'm learning about building and training FCNNs in PyTorch. I've come across the concept of overfitting. I don't know what this is, why it's caused, and why we need to prevent it. So I kind of have an idea of what overfitting is, but like I don't fully understand overfitting. So oh, then there's also underfitting, which I need to look into. But let's see what the language model says. Okay, overfitting is a critical concept in deep learning and machine learning. Below is a comprehensive explanation of what overfitting is. Wait, what overfitting is, why it happens, and why it is essential to address it, particularly in the context of training fully connected neural networks using PyTorch. What is overfitting? Overfitting occurs when a machine learning model the train learns. When a machine learning model learns the training data too well, including its noise and irrelevant patterns, to the point that it poorly performs on unseen data. Right. So this is about as much as I know about overfitting, is that if a model is overfitting, then that means it doesn't generalize on new data very well. It works really well on specifically the data that it's been trained on. That's about all that I understand about overfitting. But like now I want to get like a better understanding. An overfit model essentially memorizes the training data rather than generalizing patterns that work on new data. I feel like there's something to be explored in terms of generalizing patterns, or the concept of generalizing patterns, because this is something that I've noticed with, at least with feed forward neural networks. I'm sure even convolutional neural networks do this. I feel like neural networks in general do this to a certain extent, where they're sort of learning patterns, and at some point I want to be able to find a way to visualize this concept, the concept of, the neural network learning a pattern from like going from not knowing a pattern at all to forming a pattern that it can then follow. Okay, an overfit model essentially memorizes the training data rather than generalizing patterns that work on new data. This defeats the purpose of machine learning, which is to produce models that generalize well across various data sets. In practical terms, and in practical terms, overfitting can be identified when the model achieves high accuracy or low loss on training data, but performs poorly on validation or test data. Okay, that makes sense. What causes overfitting? Several factors contribute to overfitting. So okay, I think this is also one of the reasons why shuffling is introduced in the data set. So as an example, actually not as an example, this is literally the example. Where is it? They haven't mentioned shuffling here, but like when you're loading the data loader, the train data loader and the test data loader, you have an additional parameter, an additional argument called shuffle, or something with the word shuffle in it, and this makes it so each time you call next on the iterator, it's gonna return um, it's gonna return a shuffled set of samples. It's gonna shuffle things around and give you like new data each time. So it's kind of like getting new data each time. It's not the exact same data. So anytime you call next, you're not gonna get that exact same set of values. Things are gonna be moved around. So it introduces more randomness in there. And because of that, the model has a lot more samples to sort of learn from. So okay, something that I need to study later on is how do I say this? Something just came in my mind that like at some point later I need to study how um how do I say this? So like okay, I wanna be able to visualize the difference, be it, through Matplotlib or just visualizing it in my head. I want to be able to visualize the difference between um, not shuffling data and shuffling data, because shuffling data introduces more randomness into the data that the neural network is learning from, right? So the network learns to generalize much better, as opposed to if each time you gave it a fixed set of samples in like a fixed order, that might generate a different kind of pattern, versus if you gave it completely shuffled samples each time, then that would generate a different kind of pattern. I want to be able to visualize that pattern as well. The problem is like, not sure how you would go about visualizing these patterns. There has to be a way to like quantify it in order to be able to visualize it. If that makes sense. Um, I'm gonna have to look into what methods are available to do this with scikit-learn and matplotlib and seaborn, because I'm pretty sure seaborn might have like, higher level functions that allow us to do something similar, if not exactly that. Okay, let's come back to this. Okay, several factors contribute to overfitting. Insufficient training data. When the when the data set is too small, the model may struggle to generalize and instead memorize the training data patterns. Okay, dude, there's something to be explored. I keep saying this, I need to write this shit down, dude. There's so many things for me to experiment with and so many things for me to study and explore. There's something to be explored in the concept that the neural network it memorizes the training data patterns. Does that make sense? Like there's something to be there's something interesting about that concept. Like that's I mean, that's exactly what the training process is doing. That's the whole point of training the neural network, because initially it doesn't know anything, and then you train it on this data set, so it learns a bunch of like patterns. But there's something really interesting about the concept of like teaching this neural network, um, teaching the neural network things based on training data patterns. Okay, high model complexity. Oh, that can impact it as well. Okay, complex models with many parameters, example, deeper networks with more neurons, are more likely to fit. Sorry about that. Okay, yeah. Where was I? Example, deeper networks with more neurons. Okay, so complex models with many parameters are more likely to fit noise within data, leading to overfitting. Okay, noisy or poor quality data. If the training dataset contains noise or irrelevant information, the model may inadvertently learn these artifacts, reducing its ability to generalize. Prolonged training periods. Train. Oh, that can affect as well. Okay, training the model for two. Actually, no. This is what I was talking about. Why am I surprised at this? I actually knew this part because I was mentioning this earlier that, um, you know, we can give it more epics. So basically, train it for longer until the accuracy is like perfect and the loss is like near zero. But then you also run the risk of overfitting, and that's what's happening here. Because like it it sort of it fits the training data too perfectly, and then it doesn't fit the test data very well. Though there's something interesting going on here. Give me a second. Yeah, there's something interesting going on in this training loop, because we're not just training, we train and then we test as well after each epoch. Um, hold on. Yeah, I didn't look at the test loop a whole lot, so I don't remember what is going on here. Test error, accuracy, so and so. Okay, so the accuracy and average loss is being calculated here. I'm gonna need to look into this, like all the math that's going on here, just to understand what's being done. But yeah, okay, I kind of forgot what I was talking about, because I was like, okay, after each training epoch, we do run one test just to gauge the model's accuracy on on test data. So we're not just sticking to training data. I forgot where I was going with that though, so never mind. Um, okay, training the model for too many epochs can result in the model memorizing the training data instead of learning generalized patterns. Right. Give me a second. Um, okay, so I looked at this thing, Great Expectation, which shout out to encoders who rated us yesterday. They were mentioning about this, and this is an interesting tool. I looked into it a little bit, um, and I'm probably going to need to come back to this later on once I start doing uh, once I start working with like bigger data, then I feel like I'm gonna need to come back to this. I didn't get a chance to look at either of these, and that's why it's a good thing that I'm writing these things down. So at least that way I remember it for later. Okay, so stuff for later. Visualizing um, visualizing the learned or visualizing the patterns learned by a neural network. Um, yeah, okay. Visualizing the patterns learned by a neural network. What else was there? Shit, I missed the ad timer. Okay, there's gonna be an ad starting in, I don't know, maybe 5, 10 seconds. Uh, then I'll take a hydration break. What else was there that I was trying to remember? Oh, yeah. Um, explore the concept of a neural network. Let me just say NN. Explore the concept of an NN learning um, patterns from data. Does that make sense? I think so. Explore the concept of a neural network learning patterns from data. Maybe even visualize it. Okay, I can't remember what. Okay, all right. There's an ad playing right now, so I'm going to take a hydration break and then, well, I'll see you guys in 30 seconds. Okay, welcome back. I'm trying to remember what was the other thing that I was trying, because there's like, dude, this is what's interesting about neural networks. It's, dude, the fact that you're able to teach a neural network something, right? The neural network initially doesn't know anything, and then you provide it with data, and where was I going with this? Yeah. So initially the neural network doesn't know anything, and then you train it based on data, and then it looks at that data and learns patterns from that data based on, whatever training logic you set up. There's something really interesting about that concept. Like we are able to create these, what do you even call them? These conceptual machines, which we are then able to teach. Maybe it's just because I'm still, new to deep learning, but there's something kind of exciting and really interesting, and there's something that I feel like there's a lot to explore in this whole thing. Okay. Anyways, enough gushing about deep learning. Let's let's carry on. So, training the model for too many epochs can result in the model memorizing training data instead of learning generalized patterns. Okay, let me just copy this. Try to visualize what model memorizing the training data instead of learning generalized patterns looks like. Okay. This is commonly referred to as overtraining. Okay. Bias variance. Oh, bias, dude. I need to look into bias as well. Um, Understand why bias is necessary, or biases, because there's multiple. Okay. Why biases are necessary in a feed-forward neural network. What they do and how they can affect the behavior of the network. Okay, right. Bias variance trade-off. Models with very low bias but high variance tend to overfit since they closely align with the training data but fail to generalize across datasets. I haven't understood that bit. Models with low bias, what does low bias mean in this case? Are they talking about the bias values, or is it just the idea of bias, like the concept of bias? Give me a second. Okay. Why prevent overfitting? Overfitting is detrimental because it compromises the generalization capability of the model. While an overfit model might excel in training, it will fail to make accurate predictions on unseen data, which is the ultimate objective of machine learning. Okay. Oh, okay. Visualize um, an overfit model versus a model that generalizes well. I have no idea how I'm going to go about visualizing these things, so I'm definitely going to need to ask the language model for, ideas on how to visualize these things later on. But that's once we finish, once we finish actually training the network, and then we have to evaluate how well the model is performing. That's then. Okay, how to prevent overfitting. To mitigate overfitting, several strategies can be employed. Increase training data. Adding more diverse and high quality data helps the model capture broader patterns, improving generalization. Okay, data augmentation. Techniques such as rotating, flipping, or cropping images can artificially increase dataset size, making the model more robust. Really? Okay. Techniques such as rotating, flipping, or cropping images can artificially increase dataset size, making the model more robust. I should explore this. Um, Explore data augmentation for FCNN. Currently we are sticking to FCNN. Um, let's copy this. Where is this from? Okay. All right. Simplify the model. Reduce the number of parameters. Example, fewer neurons or layers to lower the likelihood of memorizing the training data. That's another thing that I need to uh, note down, which is test different FCNN designs, understand what increasing or decreasing Um, the number of hidden layers or the number of neurons in each hidden layer does. Actually, just so I can understand this better, understand understand how changing the number of hidden layers affects the network, and then also understand how changing the number of neurons in each hidden layer affects the neural network. I need to remember this because there's a bunch of like experimentation that I want to do surrounding feed forward neural networks. Once I've learned how to train the neural network, I wanna be able to like experiment with different designs and understand what exactly is happening and why it's happening the way that it's happening. Like if the model if I reduce or increase the number of hidden layers or reduce or increase the number of neurons in the hidden layers, and the model reacts to it in a certain way, I want to understand exactly why the model is reacting that way. Okay, use regularize. There's that word that is not easy to pronounce for me. Okay, use regularization. Techniques like L1 and L2 regularization, uh, also called weight decay, penalize large parameter values, encouraging the model to generalize better. Dropout can also help by randomly deactivating neurons during training, preventing over reliance on specific neurons. Okay, okay. Um, regularization. Actually, I don't think I need to make like, sub points for this. I can just do L1, L2, and dropout. Okay, early stopping. Monitor performance on a validation set during training and stop training when validation loss stops improving, preventing the model from overtraining. Monitor performance on a validation set during training and stop training when the validation loss stops improving. Okay, that's already being done here, right? Well, okay, no. We're not explicitly stopping it when the loss stops improving. But we are testing constantly. After every epoch, we are testing it on uh, a test data set, which I'm assuming is the same as, a validation data set. I could be wrong. Maybe I should look into that later. Give me a second. Okay, yeah. Uh, where was I? Early stopping. Okay. Cross validation. Use k-fold cross validation to evaluate the model on different subsets of data. ensuring it generalizes well across multiple splits of data sets, multiple splits of the data set. Okay, add noise to the inputs. Injecting noise into the input data or labels can regularize the model and make it more robust. Okay, improve data quality. Cleaning up noisy data and selecting only relevant features improve the model's learning process and generalization ability. All right. Okay, detecting overfitting. To recognize overfitting during neural network training, what does this mean? Training loss less than validation loss. If training data loss is significantly lower, if training data loss is significantly lower than validation loss, the model is likely overfitting. That makes sense, yeah, because if the loss is super low during training, but then when you give it new data, then the loss is still high. That means it's overfitting to to its training data. Okay, monitor performance metrics and visualization tools, example learning curves, to identify when validation performance begins to deteriorate as training continues. Okay, all right, right. Okay, these are some indicators which, yeah, this makes sense, right? If the training data, if the training loss is much lower than validation loss, then it's overfitting. If the training loss is much greater than validation loss, then it's underfitting. And if they're close to the same, then it's a good generalization. Understanding and addressing underfitting, no, overfitting, is key to building effective models in PyTorch or any other machine learning framework. By applying these strategies, you can ensure your FCNNs, your neural networks perform well not only on training data but also on data they have never seen before. Okay, let's talk about wait. Okay, what about underfitting? Okay, underfitting occurs when a machine learning. Hold on. Okay, okay. So we're probably not going to read all of this, but like just get an understanding. Underfitting occurs when a machine learning model is too simplistic to capture the underlying relationship in the data. It results in poor performance on both the training and test data sets because the model fails to learn and generalize the patterns effectively. Why does underfitting happen? Uh, underfitting can Underfitting is caused by various factors, including high bias. A model with high bias oversimplifies the data, ignoring complex patterns. For example, using a linear regression model on data with a polynomial relationship will lead to underfitting. Okay. Um, Insufficient training. When a model is not trained with enough epochs, it fails to capture the underlying trends in the data. Simplistic model architecture. Models with insufficient parameters or overly simple structures, example, shallow neural networks, may lack the capacity to learn complex features of the data. Inadequate feature engineering. Missing critical features or using features do not adequately represent the data's complexity can lead to underfitting. Over regularization. Excessive use of regularization techniques, such as L1, L2 regularization or dropout, can overly constrain the learning process, limiting the model's ability to capture patterns. A lot of this is basically just hinting at the fact that the model has not learned properly, and that's basically when underfitting occurs. It hasn't learned patterns from its training data properly, and if it hasn't learned patterns from its training data properly, then it's probably also not going to perform well on generalized data. Insufficient or poor quality data, okay. Impacts of underfitting, high training and test error. Oh, a high loss, okay. An underfit model fails to perform well on both the training and test data sets, which is evidenced by high loss or low accuracy across both. Poor generalization, yep, that makes sense. It consistently fails to capture the dominant patterns in the data, making it unreliable for real world predictions or decisions. Oversimplified predictions. The model may produce overly simplistic outputs that do not reflect the complexity of the data. Example, misclassifying diverse categories as one. Okay, all right, cool. Now, let's do a tiny bit of reading here. I might need to explore the test data set and actually even the remainder of all of this off stream. But for now, let's do a bit of reading here. Okay, now that we have a model and data, it's time to train, validate, and test our model by optimizing its parameters on our data. Training a model is an iterative process. In each iteration, the model makes a guess about the output, calculates the error in its guess, which is our loss, and it collects the derivatives of the error with respect to its parameters, and optimizes these parameters using gradient descent. Okay, all right. So then this is our code. That's the neural network. Um, oh, okay, it's the neural network and the data sets. This is the entire code, basically. Downloading and loading the data sets and then building the neural network. And then we have this. And then, okay, the test and the training and test phase comes later on. Okay, hyperparameters. Hyperparameters are adjustable parameters that let you control the model optimization process. Different hyperparameter values can impact model training and convergence rates. Read more about hyperparameter tuning. Okay. We define the following hyperparameters for training. Number of epochs, the number of times to iterate over the dataset. Batch size, the number of data samples propagated through the network. Through the parameters are what? Through before the parameters are updated. Okay. Learning rate, how much to update the model's parameters at each epoch or at each batch. Smaller values yield slow learning speed, while large values may result in unpredictable behavior during training. Okay. Optimization loop. Once we set our parameters, we can then train and optimize our model with an optimization loop. Each iteration of the optimization loop is called an epoch. Each epoch consists of two main parts, the train loop and the test loop. The train loop iterates over the training data set and tries to converge to optimal parameters, and the test loop iterates over the test data set to check if the model performance is improving. All right. Let's briefly familiarize ourselves with some of the concepts used in the training loop. Jump ahead to the full implementation. Okay, all right, that's fine. Loss function. When presented with some training data, our untrained, I mean, we don't, okay, so we don't need to read about cross entropy loss specifically because we studied that yesterday, but just in general, hold on, words. Just in general, holy shit, just in general, I would like to get an understanding of the concept of loss functions because there's a couple of other loss functions as well, and I haven't used any of those. Actually, okay, this says negative loss, negative log likelihood loss, um, which is part of cross entropy. Yeah, there you go. Cross entropy loss includes negative log likelihood loss. Okay, when presented with some training data, our um, our untrained network is likely to not give the correct answer. Loss function measures the degree of dissimilarity of obtained result to the target value. And it is the loss function that we want to minimize during training. Okay, I remember back when I was learning, when I was getting into machine learning, I found the terminology kind of confusing because I didn't understand the meaning of minimizing the loss function. This is something that I've noticed a bunch of people saying, but like at the time it didn't make sense to me. In reality, what they're trying to minimize is just the loss itself, but they say, they're minimizing the loss function. And also, when you're calculating gradients, the gradients are being generated for the loss function, which again, even there, the terminology, it was kind of confusing for me because I'm not used to, anytime I say function, it to me, it's just like a set of instructions that's executing from the start to the finish, right? So it enters the function, executes the instructions, and then exits the function. But then something being a function of something else, like that just wasn't, I, I I didn't know how to think of functions in that way. Like that's the mathematical way of thinking of functions. Usually in programming, you don't say, this is a function of that, unless you're talking about a function belonging to a class or something. So yeah, initially it was a little bit confusing for me understanding the terminology and understanding what exactly was being said. Um, Also, optimizing the loss function. I think that's another way of saying that they're trying to minimize the loss. Yeah. Okay. So that was just like a random memory that I had, a random like, because like back when I was learning, so I didn't start by learning deep learning. I initially started by learning machine learning, right? And then I was led to supervised learning, and then in supervised learning, the first thing that I came across was linear regression. So I started learning linear regression, and in linear regression, I was coming across a bunch of these different terms, and I was like, hold on, dude, what what does this mean? What does that mean? Okay, common loss functions include. Wait, hold on. Did I finish that? Okay, loss functions measure the degree of dissimilarity of obtained result to the target value, and it is the loss function we want to minimize during training. To calculate the loss, we make a prediction using the inputs of our given data sample and compare it against the true data label value. Okay, common loss functions include mean squared error for regression tasks, negative log likelihood loss for classification, and cross entropy loss, which combines log softmax and negative log likelihood loss. Hey, Sarah, welcome to the stream. Hello, hello. How's it going? We are learning how to train a neural network, doing a bit of reading here. So, we pass our model's output logits to cross entropy loss, which will normalize the logits. Hold on. Okay, so this says log softmax, but then we are also using negative log likelihood loss. So where's the log for log softmax? Like, is there a log operation happening here as well, or am I like missing something here in like in terms of what what log means in log softmax? You're existing? Hell yeah. That's awesome. That's awesome. Give this a second to load, and then we can continue reading. Oh, hold on. Wait, am I about to have some PC issues? Um, okay, let's just hope that the thing loads. Okay, we pass our model's output logits to cross entropy loss, which will normalize the logits and compute the prediction error. Okay, all right. Normalizing the logits, basically just passing it through softmax, okay, and then computes the prediction error, which is our negative log likelihood loss. Okay. Oh, there's one more thing that it does. It then does like what it calls, I think, batch wide normalization. No, batch wide. There was batch wide something. I forgot what it's called, but like basically, if you're passing it a batch, it takes the average of all of those loss values, so it can then output one value as opposed to, wait, what is this text? Oh yeah, this is just what I was typing. Yeah. Um, Shit, I lost my train of thought. Um, I think I was talking about, yeah, it gives you the average of multiple loss values. Um, so it's giving you one value as opposed to multiple loss values. Okay, optimizer. Optimization is the process of adjusting model parameters to reduce model error in each training step. Optimization algorithms define how the process is performed. In this example, we use stochastic gradient descent. All optimization logic is encapsulated in the optimizer object. Here we use the SGD optimizer. Additionally, there are many different optimizers available in PyTorch, such as Atom and RMS Prop, that work better for different kinds of models and data. Okay, we initialize the optimizer by registering the model's parameters that need to be trained and passing in the learning rate hyperparameter. Okay, yeah. Model's parameters in this case are the weights and biases, and then the learning rate is what we specify. Okay. Inside the training loop, optimization happens in three steps. We call optimizer.zeroGrad to reset the gradients of model parameters. Gradients by default add up. To prevent double counting, we explicitly zero them at each iteration. Okay, backpropagate the prediction loss with a call to loss start backward. Okay, PyTorch deposits the gradients with the gradients of the loss WRT. I need to look into what that is. Each parameter. Oh, the loss with respect to. I think that's what it means. gradients of the loss with respect to the parameters. I think that's what WRT means. Oh yeah, it says that. It says that with respect to each parameter. PyTorch deposits the gradients of the loss with respect to each parameter. Once we have our gradients, we call optimizer.step to adjust the parameters by the gradients collected in the backward pass. Okay, all right. Did this load? Okay. Things are kind of freezing on my system. Right, so this mentioned two different things, right? This mentioned, actually, maybe I could look into it like separately. Yeah, maybe I could look into which one was it that I was, oh, log softmax. Okay, um, full implementation, all right. We initialize the loss function in optimizer and pass it to the training loop and test loop. Feel free to increase the number of epochs to track the model's improving performance. Okay, and then after that we are done. Okay, so that is our optimization step, which I still need to look into. I still need to look into the test loop. But before the test loop, I need to look into the training loop, finish the training loop, because this still we still have to do the backward pass. We still have to update the weights, and then I mean zero grad is just zeroing out the gradients. But yeah, we still have to do this part of the training loop, and then also every 100 batches we need to record what the current loss is. Okay, all right, now hold on. Give me a second. You know what we are going to do? We haven't rated Oz in a while. Oz is a friend. Oz is cool people. Um, she's a she's a game developer and a gamer and just like a variety streamer. She's currently working on reworking the visual novel system in her game, and then maybe she's gonna play Monster Hunter later on. So we're gonna raid Oz. These days I don't get much of a chance to raid Oz, so I'm glad that I'm getting a chance today. We're gonna raid Oz, and hopefully I get a chance to stream again tomorrow. Hopefully I get a chance to do another talking stream tomorrow. Today's stream is a little short compared to the usual streams because unfortunately I started a little bit late. That's completely on me. Hopefully tomorrow I'm gonna start on time and maybe we can go for like 2 hours again, just like yesterday. Let me see how much of this training logic I can finish before tomorrow's stream, and then let's see where to go from there. Sarah, thank you for stopping by and saying hello and hanging out. Anyone else who might have been lurking in the chat, thanks for hanging out. I appreciate you guys being here. But that being said, I hope you guys have a nice day, and I'll see you all next time. Peace.